Hello, welcome to Module 2, Classification for DSBA ITCS 6156. This week we're going to talk about different types of classification algorithms. By the end of this module, you should expect to be able, or I expect you to be able to list and describe some of the various types of classification algorithms and also provide examples of each of these types. Be able to describe how they work and be able to choose which algorithm is best, with big air quotes around it, for different types of problems that you're looking to solve. I also want you to be able to list some of the standard performance metrics for classification algorithms. These are things that you're going to be expected to do when you run a learning algorithm and provide the output to your consumers so that the consumers can understand how effective your algorithm is or your implementation model is. And I also want you to be able to determine how good a classification system performs in terms of these performance metrics. So this is going to be things like your confusion metrics, being able to describe the sensitivity of an algorithm, being able to describe the recall ability of an algorithm or a model. So there are three types of classification systems that we're going to address in this model. The first is a simple binary classifier. This determines a membership in a single class. So you're either in the class or you're not in the class. You're not defining membership among multiple classes. This is usually meant to be a fairly crisp boundary for membership. And what I mean by crisp boundary for membership in this case is you have everything in the world that's inside of Class A, and everything else is not in Class A. Now, the challenge with this is that we're going to see is that there's noise in models, there's noise in data sets. So this isn't always going to be this nice idyllic boundary where we can describe something truly being in a class or not in a class. So this crispness is up for debate. We also have multi-class classifiers. So in this case, what we end up with is, in addition to Class A, we have other classes that something can be a member of as well. And typically the way we do this is by training a whole bunch of binary classifiers. So something is either in the class or it's not in the class. And by it not being in the class, that might mean that it's in one of the other classes around it, or it's out here somewhere in none of the classes. So when we define these groups of binary classifiers, what we're doing is saying it's either not in A or it's in A, it's not in D or it's in D, etc. Taking the value, the predicted value of each one of these binary classifiers and looking at the outputs and comparing them and picking the best one. So maybe it's not 0 completely, maybe it's not 1 completely, but that value, that predicted value, is most like Class A. So that's the one that ends up getting predicted in terms of this operation. So we do this using a number of different strategies. We can do this using what we refer to as a 1 versus 1 strategy or a 1 versus all strategy. and these have different pros and cons. So, a one versus one strategy means that I train a whole bunch of binary classifiers not to be in A or not in A, but basically it becomes A versus B. It becomes A versus C, B versus C, so on and so forth. So what I end up doing in this case is I train a whole bunch of binary classifiers. In fact, I train n times n minus 1 over 2 binary classifiers to determine what the best match is in this case. So if I've got all of these one versus one classifiers and I execute all of those models and I come back with this B versus C, saying it's most likely in B, and that's the highest value that any of the classifiers returned, I'm going to say that my input is in class B. So I've got a couple of different things here. I've got a much better discrimination in terms of something being in a class or not in a class by comparing all of the different things that it could be in. But I'm also training a whole lot more classifiers. So that is time expensive in terms of compute time expensive in terms of the number of classifiers that I have to train. It is compute time expensive in terms of operations, because for every input I have to evaluate it against every one of these one versus one classifiers. It's potentially memory intensive depending upon how I run these things. If I run them all sequentially, it's probably not so memory intensive because I allocate all of the memory, run the algorithm, take a score, clear the memory, populate it, run the algorithm, compute a score. But by doing it sequentially, my execution time is the sum of every one of these classifiers. So I've got a very long running problem in that case. If I do it in parallel, I can potentially shrink my execution time to being whatever the maximum time of any classifier is. And that will be my overall execution time for the algorithm on average. So this can be computationally expensive. My other mechanism is a one versus all type classifier. So in a one versus all type classifier, what I'm doing is training a whole bunch of these binary classifiers of in or not in, and then choosing the one that has the greatest value out of it. So in this case, where it was B versus C had the highest value, perhaps in this case, NB had the highest value, and that's the one that ends up getting selected for the actual membership of the component. So another type that I have to work with are multi-label, multi-output type classifiers. These are similar to multi-class, but the outputs are not mutually exclusive. So there are some cases here where I can classify a person. So I can classify those people, that person, and assign one layer, or one label rather, for physical gender. I can assign another label for eye color. I can assign another label for shoe size. So I can output multiple labels in this case um, that describe the same person in a lot of different ways. Um, I can use these sometimes for fuzzy set implementations where I'm unable to determine a clear membership in a case. So in this case, if I want to determine is something small, medium, or large, um, maybe I go through and define some guidelines around what small, medium, or large means, but there are overlaps to a certain extent because nothing ever seems to be perfect. If you've bought clothes, you know this. So, what I look to in this case is trying to figure out if it's very, very, very small but not so medium. Maybe I'll put a 0.9 likelihood of it belonging to the small class, and I'll say maybe it's 0.4 for belonging to the medium class. Same thing over here. It's on the small end of the large spectrum, but it could also be on the high end of a medium spectrum. So maybe I assign both the medium and the large label to it, but it's more large than medium. So there's a lot of different nuances to how we can use classification systems when we're building models. So there's caveats that we need to look at. The first one is the same algorithm can be used for multiple different types of machine learning activities. So you can't, like I said, put together a truth table of, for this type of a classification problem with these types of inputs, I always use this algorithm. You will find over time that you will use different types of algorithms for different types of predictions. Sometimes you will combine different types of algorithms in order to achieve the same result. And we'll look at this when we start talking about ensemble methods later on. And because of this, it's one more reason you need to understand both the domains of the problems that you're working with, as well as the domains of the problem that the algorithm can support, as well as the applicability and the shortcomings of each of the methods, so that you don't inadvertently make some type of a modeling error as you're building and designing your systems. So binary classifiers, there are a lot of different kinds of binary classifiers. We're going to touch on a few of these in this course. We can't cover the entire set because there are just too many of them to cover in any way, shape, or form. So some of the most common ones are naive Bayes classifiers. These are statistical classifiers that basically say, given a set of feature values for my different inputs, what's the likelihood that one of these instances is the member of a class? So you may or may not be familiar with seeing something in statistics like, go back to the pen down here, like the probability that something is X given that it has different parameters put into it. So in this case, what's the probability that it's X given feature Y1 and Y2 and Y3? So these are prediction or probability type classifiers. Nearest neighbors are another type of classifier in which we look at collections of data in the system. I'm just going to do a couple of these just to keep it simple, where we look at different collections of data in the system. And then when a new value pops up, what do I do with it if it's right here? So in a nearest neighbor type classifier, each of the groups evaluates the closeness of this input's features to its internal features. So I end up with a model for the red set, a model for the magenta set, and a model for the green set. And I execute this new value against each of those models. And what I find out is that it's most like the red set, maybe. It's somewhat like the magenta set, and it's very little like the green set. So the membership of this new point that gets classified as red. So these nearest neighbors basically evaluate, is something close enough to be a member of a class. And y'all looked at this during the a little bit during your first programming assignment of using the nearest neighbors class in scikit-learn. And then logistic regression. Logistic regression is similar to linear regression in that you're predicting a value on a continuum, and typically we're viewing that value on that continuum as a sigmoid function. And what you want is anything that's predicted by the model above this 0.5 value for y is predicted to be in the n class, so it's true. And anything that's below this 0.5 threshold gets predicted into the not in or the false class. So if we look at this, basically we're saying for a set of input features X. So this is a big X and it's in bold. So when you see that going forward, you need to realize this is a matrix of values. So this is a collection of feature vectors in a matrix form. So I have an m by n matrix where I have m features for each instance of data, and I have n instances in the matrix. So what you'll see is this will look something like M1, N1, Mn, N1, so on and so forth. Y'all have seen matrices before. So we use a Bernoulli distribution in this case because a Bernoulli distribution is identified towards binary classes. So the Bernoulli distribution is looking to predict the range of something being between the probability that something is between 0 and 1 in the output. So we check to see if for a given matrix of data, do I expect a new value y to be either in that class given the distribution of the matrix X. So if we look at this a little bit more, Um, we'll talk about this soon. So, logistic regression is really a classification method, even though I'm predicting a value on a continuum. And what this is saying is I'm predicting a value between 0, well, that didn't work. I'm predicting a value between 0 and 1. And let me change that to something that will show up on white. Between 0 and 1 for a given value of x. So my prediction of y. So when you see this hat over the top of any variable, that means it's a prediction. So this will be the output of your model. For a given function, so in this case, I'm using a logistics function to predict an output. So sigma t, which in this case will be my x vector. So even though on the other page I was dealing with this matrix X of values, the matrix X is basically a set of vectors of training data of n vectors of instance data. So for each one of these values here, I'm evaluating the logistics function with each of these to determine what this predicted value is between this on this continuum between 0 and 1. And if that value is greater than 0.5, that means that it should belong to the true class. If it's below 0.5, it should belong to the false class. And if you remember from us talking last week, this bend in the knee here of this function is defined by this value k in the logistics function equation. So if I make this value of k very, very large, and by very, very large, I mean about 20, what this does is it takes this logistics function and makes a very sharp boundary for it to determine whether something's in the class or out of the class. Now, if I look at an example from the Murphy book for machine learning, I see my sigmoid function here, and I know from our prior discussions that what I want is to not do that. What I want is to be able to say, for this cutoff point, something is cleanly not in the class or something is cleanly in the class. But if I look at this example from page 21 in Murphy, I see where some of the caveats for this are. So outside of this yellow box of uncertainty, this yellow box of doom, the function works the way you would expect it to. So as I'm predicting using various instances of data from the X matrix of input instances, they end up in the class that you would expect. So for certain values, they get driven down to 0 for not in the class. Notice that I've got all these black dots down here at 0. So that's the false instance. And beyond a certain range, I end up with them being driven up in the true membership, and that one's right on it. So these are the in class membership ranges. But inside of this yellow box of doom here, I end up with a problem. So this value, which is about 525, if I remember right, it has two different predictions for the same value from the data set. So for one value of 525, the function predicts it's not in the class. But for the other value of 525, it predicts that it is in. So now we start to see something that looks like error in the predictions. So now the next value, which is 530-ish, let's say 532 just to be funny, it's predicted out of the class and is correctly predicted out of the class because this y value is below this 0.5 cutoff for membership. Then when I start getting above 0.5, once again, it's doing what you expect it to do for the most part until you hit another one of these cases where the true value of the class is not in, but the algorithm predicted it in. So these red dots are our predictions. So once again, it's doing fine until it's not. And then after that box of doom, everything's working exactly the way you would expect it to. So you end up with a certain amount of false negatives not in the class. You end up with a certain number of false positives where it predicts it in the class, but it's really not. And that's part of your error for your model. That's part of your performance metrics that we'll talk about in a little bit. So logistic regression returns a value on a continuum just like linear regression does or any other type of regressions do. But they're a classifier because they're either in a range or they're not in a range. So that's what makes this a classifier. So binary classifiers, there are other types, support vector machines, which we're going to devote the entirety of Chapter 5 to. Classification and regression trees, these are referred to as CART models or decision trees sometimes. Once again, we devote an entire chapter to that in Chapter 6. Then earlier I spoke about ensemble methods where we add different types of classifiers together. These are referred to sometimes as bagging and boosting and random forests. We're not going to worry about what those terms mean at the moment. So we'll talk about that when we get into Chapter 7 and devote a reasonable amount of effort to that. So multi-class classifiers. Once again, we've already talked about this in fairly good detail, but this is where we extend binary classifiers for each class to evaluate membership in more than one class. So in this case, instead of, in this case, saying something is a dog or it's not a dog, we train a bunch of individual classifiers for each class being evaluated. So say dog, cat, person, toaster, etc., and then run the input against it. So is something a dog? Is something a cat? Sometimes that can be a little bit tricky. A dog or a cat versus a person. What if the person is wearing a cat suit? Have you trained the model appropriately to determine somebody wearing a really good cat suit versus an actual cat? Toaster, we talked last week about the case where somebody was fiddling around with Google Brain and putting a sticker on things and it made everything a toaster. So you've it's not as straightforward as you would think it would be. We talked about one versus all, so where we basically go through and sorry about that. We basically go through and train a classifier for each class, and then whichever classifier generates the highest probability or highest likelihood that something is a member of that class is the one that wins. And then the one versus one method where we train all of these classifier pairs and do a winner takes all uh, classification as a result of all of these different evaluations. We talked about the n times n minus 1 over 2 number of classifiers that you have to train. And once again, this just really doesn't scale well when you get into large numbers of features. Multi-label, multi-output, we talked about a little bit. So multi-label enables us to create a classifier that can assign multiple labels to an input. So I throw a picture up on the wall. It contains a cat, a dog, and a toaster. Hopefully this thing will appropriately go through and return the labels for the picture that say, yep, yea, verily, there's a cat, there's a dog, and there's a toaster in the picture, not a cat that looks like a toaster. Multi-output is an extension of multi-label, and we talked about this a little bit before, where I can return multiple values for each label. Big dog versus a small dog, a car that's a sedan or a sports car, and also where I've got multiple labels for the same value. Whether a shirt is red or blue, or whether a shirt is a pullover or a button up. So similar type outputs for a multi-output classifier. Nearest neighbors works very well for these types of classifiers. Gets to be a little fuzzy, like we talked about before. What differentiates a big dog from a medium dog from a small dog? It starts to get a bit muddy into how good this classifier is. So in this case, what I end up with is, and don't laugh at my dog when I do this, what ends up here is I end up with my little dog. It kind of looks like a rat, doesn't it? Versus my medium dog. Looks like a sheep. Okay, great. And then a big dog. I'm not going to continue this on. At some point in time, there's a fuzzy area in here, a fuzzy boundary, that something is a big small or a small medium, and I may make a certain amount of error in this area versus an expert. So that's where we have to be kind of careful in choosing qualitative type outputs as opposed to quantitative type outputs. So performance metrics for classification algorithms, these are some of the common ones that we use. True positives, this is where the model correctly predicted the value for a binary classifier. So if I'm talking about labeled data, the expert in this case said it was true, and the prediction for the model yielded true. So true and true equals true. So in that case, I ended up with a good answer, a good prediction. False positives are predictions where the model incorrectly predicted something to be true when in fact it was actually false if you look at the labels assigned to the data by the experts. So in the case of a false positive, I overstate a particular case. So we'll talk about why I don't like this for certain cases or why I might like this for other cases. False negatives. The model incorrectly predicted a false value when it was actually labeled true. This is referred to as a missed detection. And you see these a lot when you start talking about medical diagnostic tests and things like that. So perhaps my test of looking at a CAT scan image and determining automatically whether something is a small tumor or not a small tumor. Is it better for me to predict that something that isn't a tumor is a tumor? Or is it better for me to not predict something that is a tumor as not a tumor because I'm not certain enough? You got two different outcomes there. If I'm predicting too many things to be a tumor and follow-up tests indicate that they're really not tumors, what I've done is I've basically scared somebody needlessly. But I have at least validated through follow-on testing that person really doesn't have cancer. So what's the flip side of that? Well, I'm really not certain that this is cancer, so I just say you don't have cancer. And then later on, this thing develops into a tumor, and it could have been dealt with at a much earlier stage, at a much higher level of success. So what you're trying to do here is balance that when I'm predicting on this curve, I'm predicting with an appropriate level of sensitivity that anything in this range of uncertainty is what I want to push up to the true case so that I can do more detailed testing, detailed diagnostics, and that anything below a certain threshold I want to drive down to zero. So most likely or more likely cases that could be cancer, I want to put in the true class and then deal with them. But I don't want to needlessly take somebody who doesn't even have a tumor. Nothing shows up in the image, but for whatever reason, my algorithm says, oh, wait a minute, you've got a tumor. No, you don't. You don't have anything. But I've needlessly scared you now. Because what happens if I do this a lot? If I do this a whole lot, people turn around and say, Rob's test is junk. I just won't even get the test at all. And if I don't get that test, I'm missing out on all the cases where it's very effective in predicting tumor existence. So this has to do with the quality of the testing results and how believable the overall thing is. So this is where I start looking at these rates down here, true positive rates. This is referred to as sensitivity, recall, hit rate. Basically, the number of true positives predicted by the test versus the number of true positives plus the number of false negatives predicted by the test. So if we look at this thing as a square, and I've got my predictions, I'm going to put these in the wrong order because I always get these wrong, versus my true results. So if it really is negative and I predicted negative, I've got a true negative in this case. So if I have, let's see, if I predict a positive and it really was positive, I've got a true positive. So in this case, for true positive rate, what I'm worried about is the case where I predict a negative, excuse me, I predict a negative, but it is truly positive. So in this case over here, I've got a false negative because it should have been true, but I predicted false. So if I want to look at my sensitivity here, I'm taking all of these positive, taking the positives and the false negatives and checking the ratio of those. So for true negative rate, once again, I've got my true negatives and my predictive false positives, and I look at this ratio versus the number of true negatives to determine how specific my results are. And these two are at odds with each other. As I increase the sensitivity of the model, at some point I have to start decreasing the specificity of the model. Because if you look at these things, they're inversely proportional curves where there's a limit right here where these two lines cross. That's as good as this model can ever get. If I want to increase my sensitivity of this model, by definition, my false negative rate is going to have to go down. But when my false negative rate goes down, the only way I can do that is by predicting positives more frequently than necessary, and vice versa. If I want to increase the specificity of my model, I end up having to decrease the number of false positives. But what I'm doing at some point, above some point, which is this intersection right here, the only way I can decrease the number of false positives is to predict more false negatives. So these are at odds with each other, and you need to understand when somebody says, I want something to be 99.9% sensitive to detecting when there's cancer, what that may mean is that I am more frequently than not, or I'm more frequently than not detecting a false positive. So there's this is something you need to kind of play around with and get a feel for. False positive rate is just what you think it is. The number of false positives issued by or predicted by the model divided by the sum of false positives and true negatives. So these are my false alarms. So if I'm predicting false positives and it's always false positive and never a true negative, basically I've got 100% false alarm rate. If I'm predicting a false positive and it's really a negative in that case, what happens here? So I'm saying it's positive, it's really negative. As this happens, I'm predicting something to be positive when I know it's really false. So this is also referred to as type 1 error in my statistical analysis. Once again, the precision and recall formulas. We have something we refer to as an F1 score, and basically what an F1 score is it measures what's referred to as the harmonic mean between precision and recall. So this is my number of true positives divided by my number of true positives plus the sum. Come on. Back. Come on. Where are you? Okay, let's try this again. So this is my number of true positives plus the number of false negatives plus the number of false positives divided by 2. So why is this divided by 2? So what we're doing here is we're looking for this mean or this average. So if I have no false negatives and no false positives, what this is simply the ratio of true positives divided by true positives equals to 1. That means I've got basically a completely precise model here. So if I add in the number of false negatives and the number of false positives, I've got 2 different classes here that I'm working on. So I divide by the number of classes there so that I get the average of that error. So if I increase my number of false negatives, this number starts to get bigger than just this number here. So this F1 score starts to decrease as a function of false negatives and false positives. So when I'm looking at this, what I'm trying to identify is how precision and recall affect the performance of the model. So as I was saying earlier, there's what's referred to as the precision recall trade-off. And I showed that there's this recall line in the model and the actual precision line in the model. And above a certain point where these 2 lines cross, at that point I am sacrificing one metric for the other. I am either overstating or understating true positives, or I'm understating or overstating false positives or false negatives. So we need to understand when we're building models that a perfect model is something that we're not really going to see ever, because our data is seldomly perfect. We seldom have linearly separable classes of data. If I have nice 3 classes of data here, and there are really nice broad boundaries between them, it's very easy for me to build classifiers that are highly selective. This pretty much never happens for a lot of different reasons. There are different types of error where we sample data incorrectly. So maybe instead of this being a nice clean line, it's more like a sock. And these do this in various ways where there are class overlaps. And we no longer have these nice clean boundaries which lead to errors like we were looking at before. So count yourself lucky if you end up in a situation where you have these nice crisp boundaries. But if you've got that case, you probably weren't hired for the job in the first place to derive this model. So there's this thing that we refer to sometimes as a receiver operating characteristic, or a ROC curve. And this comes out of early radar research, where they were trying to establish how effective a radar system was at predicting whether the radar was correctly seeing something or not. So if we look at this curve here, we see something that's plotted on two different axes. The y-axis in here is the curve of the true positive rate. The x-axis is the curve of the false positive rate. So what is the rate at which the model or the classifier identifies a false positive versus it identifying a true positive? So if we look at how this thing might flesh out here, that's not what I wanted. And so if we're down here on the receiver operating characteristic curve, that it's it never predicts a false positive, and it also never predicts a it never predicts a true positive, and it also never predicts a false positive. What does that mean? That means basically every prediction that the model produces is a negative case. Useless classifier in that case. What about a model in the case where it always predicts a positive? So it predicts positive when it's negative. It predicts positive when it's not negative. Basically, similar kind of thing here. We're looking at it where it's always generating a prediction of 1 in that case. And the receiver operating characteristic curve almost always has this line on the diagonal across here. And what this means, and if you look at the diagram here, it's got a line that says that's worthless. And what that means is 50% of the time, this thing is going to predict a true positive, and 50% of the time, it's going to predict a false positive. You get a better result flipping a coin than you do running this model to predict a value. So what we want to do is have as much of this area under the curve as possible for our classifier. So in that case, what we really look at, or in addition to this, what we really look at is a metric referred to as area under the curve. So when I draw this rock curve, the more area under the curve, the better my the better my classifier is, because this area up here really becomes what we look at in terms of the error of the model. So if I'm able to continue to draw that, able to continue to move this boundary up, the better my model becomes. So all of these things that we just talk about culminate in something referred to as a confusion matrix. And this is a common tool that's used to determine how well a classifier is performing. And this is exactly what we were talking about before, where I draw this 2x2 matrix and I compare actual positive and negatives from the data to the predicted positives and negatives from my model. And I come up with these specific cases where I've got my true negatives, I've got my true positives, and then I am able to use the true values versus the false values to calculate the recall of the model. Once again, the number of true positives divided by the number of true positives plus the number of false negatives. And the precision, which is the number of true positives divided by the number of true positives plus the number of false positives. So if I'm generating false positives, my precision goes down. If I'm generating false negatives, my recall goes down. And as we drew on the on a prior slide, at some point in time, I can only get so good before any increase in precision results in a decrease in recall, and vice versa. So that's our lecture for this week. I'm going to open up a thread in Canvas so that we can discuss the material from the lecture, and we will touch on it in an abbreviated version in our next class. Thank you.